So today we're going to talk about optimization problems. And so if you remember back to chapter 2 when we discussed related rates, okay, this is similar to related rates. So let's go ahead and look at these guidelines, and then we're just going to jump right in with an example. We're going to look at quite a few examples, so hopefully you'll have enough to rely on for your homework. So first of all, we need to identify all given quantities and quantities to be determined. Okay, that is the very first step. If possible, make a sketch. You might not need to. There will be a few that we use a sketch with just to kind of help things make sense. It says to write a primary equation for the quantity that is to be maximized or minimized. A review of several useful formulas from geometry is presented inside the front cover. I've given you those. That is those 4 sheets of paper that I gave you. So you're going to probably have to rely on those for some formulas. Reduce the primary equation to one having a single independent variable. This may involve the use of secondary equations relating the independent variables of the primary equation. In fact, you will pretty much always write a secondary equation. Determine the feasible domain of the primary equation. That is, determine the values for which the stated problem makes sense. So basically, when it says feasible domain, a lot of these you can't have a negative number. So if you find a negative number, you have to throw that solution out and only use the positive solution. And then step 5, determine the desired maximum or minimum value by the calculus techniques discussed in sections 3.1 through 3.4. So basically, all we're doing today is finding maximum and minimums. That's all we're doing. So the steps to find a maximum and min are the same steps that we used when we had increasing and decreasing functions. Okay. So let's go ahead and look at example 1. Find the maximum value of z if z equals xy, where x plus y equals 30. Now, I'm going to tell you right now the primary equation is z equals xy. And generally, the primary equation does not equal a value. The primary equation equals a letter. So in this case, z equals x times y. Our secondary equation is x plus y equals 30. So what I'm going to do in the secondary equation is I'm going to go ahead and solve that for x. Is there a reason why I chose x over y? No, just because x comes first alphabetically. You could have also solved it for y, it doesn't matter. Now what I'm going to do with that x value is I'm going to plug it in right up here into the z equation. Okay, so z equals 30 minus y times y. So let's simplify that. What does that give me? Good job. 30y minus y squared. Now, if you remember, if I had a function... Oh, sorry. I was jumping ahead. Because that actually leads me into what I was just going to talk about. So I was kind of thinking ahead there. If you remember, when we had increasing and decreasing functions, I started with a function. So I'm starting with the function right now, and that function is this. So if I wanted to find the extreme values of a function, what I would do is find the first derivative first. And that's what I'm going to do now. Let's find the first derivative. And what is the first derivative going to be? 30 minus 2y. So I found the first derivative. Now what I would do is find my critical numbers. So the critical numbers occur where my first derivative equals 0. So I'm going to set it equal to 0. And some of you might be able to look at this and see what values of y work. Otherwise, you might just have to solve the equation. If I add 2y to both sides, I get 2y to equal 30, which in this case, I get y to equal 15. So now, once you find that y equals 15, you're going to plug it in right up here. So what value of x do you get? 15, because it's 30 minus 15. Now it says find the maximum value of z. Well, we've already found that x equals 15 and y equals 15, but what they want in this case is they want the maximum value of z. So in this case, I'm going to take my 15 times 15. So the maximum value of z is 225. So the only difference between the increasing and decreasing functions is that you don't have to actually make the chart. Whatever value, whatever critical number you find here is going to be your answer. Okay, so I mean it's along the same process. So we're going to look at another one. This one says find the minimum value of p if p equals x squared plus y squared, where x minus y equals 40. So now what we need to do is take that primary equation, that equation that has p in it, and I need to get it in terms of one variable like I did on the problem before. So I'm going to solve this one for x. X equals 40 plus y. And then now I'm going to plug that in to my equation right there. So now remember, before we find the derivative, let's go ahead and FOIL this out. You're generally going to find a lot of these. It's going to be pretty easy to find the derivative. So let's go ahead and FOIL that out. So remember to FOIL that out. I take first term squared, which will be 1,600, twice the product of these two, 80y, plus last term squared. Yep. So one other thing I'm going to do before I find the derivative is I'm going to combine my y squareds. So really my function is 1,600 plus 80y plus 2y squared. So now what should I do? Find the derivative. So p prime equals 80 plus 4y. Next step is to set the derivative equal to 0 and essentially find my critical numbers. So, yep, I get negative 4y to equal 80, and then I get y to equal negative 20. So let's go ahead and plug that in up here. And so what do you get x to equal? 20. So now the question is, it says find the minimum value. So it doesn't just say find x and y, it says find the minimum value. So p equals x squared plus y squared. So I'm going to go ahead and plug in 20 for x and negative 20 for y. So what does that come out to be? 800. No, it's negative because you subtracted the 4y over here. No, it doesn't matter because remember in a graph the minimum can be a positive value. I mean if your graph was something like this, your minimum could be located way up here. Is the minimum? No, pretty much no. Because you're going to be doing the same steps every time, you don't change. All right, so now we get to the problems that you're actually going to have to write some equations. Okay. So a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So first of all, keyword, maximum volume. So I need to think about a box. Okay. I know that the volume of a box is length times width times height, but there are 3 variables there. So I don't want 3 variables, so I have to look throughout the problem and see if there's anything else in this problem that I'm missing. It says, what? A square base. Key thing right there. So if I draw a box with a square base, that's pretty much like x times x, right? And then I've got my height here somewhere. So I'm going to call that h. So if I wanted to find the volume of that box, it would be length times width times height. But in this case, it's going to be x times h, or x squared times h. So that's why it's really important that we notice it says a square base. That's my primary equation. Now my secondary equation is going to deal with the surface area of 108. So now I need to figure out the surface area. So first of all, surface area is the area of all the surfaces. So in this case, the area of the base will be what? X squared. Now I need to figure out the area of all of the sides. And there are how many sides? 4, and each side has an area of x times h, because length times width. Now the other thing is we're actually done. It's not going to be 2x squared because an open box, which means you don't have to worry about the top. Okay, so the open basically means there's no top. So my secondary equation will be this. Okay, now this is one thing you might want to file away to memory. An open box will always have a surface area of x squared plus 4xh. An open box will always have a volume of x squared times h. Okay. All right, so now I need to solve for one of the variables. And so if I look at my secondary equation, I'm not going to solve for x because it's going to be virtually impossible because I've got 2 of them. So the only other option is to solve this for h. Okay, so I have to get the h all by itself. So the first thing I'm going to do is subtract my x squared. So I end up getting 4xh equals 108 minus x squared. Now how do I solve that for h? Divide by 4x. Now what a lot of people do here is they try to divide things individually. We can talk about that. I don't know if I would really divide right now. Okay, I think we're good because what's going to happen is we're going to now plug this in right here for h. So my volume is actually going to be x squared times 108 minus x squared over 4x. Now the key to this problem, I'm going to warn you, is to try and simplify as much as you can before you find the derivative. Because otherwise, yeah, it could get kind of messy. So the nice thing you notice is that you have an x in the denominator right here, right? And I have an x right here, so I can actually get rid of that. So far, so good? So really, if I distribute my x now, I end up getting 108x minus x cubed, all divided by 4. Now there's one other thing I can do right now that would make the problem just a hair easier before I find the derivative. I'm going to divide each of these by 4. Okay. So what is 108 divided by 4? 27. So I have 27x minus 1/4 x cubed. So now by doing all that simplifying, you now notice I don't have to do the question, I don't have to do any of that. I'm going to go ahead and find the derivative and then set it equal to 0. So what's the derivative of 27x? 27 minus 3/4 x squared. Good. So now I need to set the first derivative equal to 0. So I'm going to go ahead and assume that I have this equal to 0 right now. Okay. And then I'm going to go ahead and add 3/4 x squared to both sides just because, one, I'm running out of room. Okay. So to solve that for x, I'm going to need to go ahead and divide by 3/4 or multiply by 4/3. Now if you're using this on your calculator, you could actually take 27 divided by 3/4 or divided by 0.75. But I get x squared to equal 36. So now to solve that, I'm going to take the square root. Now normally I take the plus or minus square root, right? It doesn't make sense that I would have a negative side. Because x is a side, right? So it doesn't make sense I would have a negative, so I'm just going to use the positive. So I get x to equal 6. Now what I'm going to do is come over here and plug it in to find my height. So I have 108 minus 6 squared over 2 times 6, which is 24. Oh, 4 times 6, sorry. I said 2 times 6, but I wrote 4 times 6, so. So here we end up having 72 over 24. So your height is 3. So let's look back at the problem. It says, what dimensions will produce a box? So the dimensions in this case will be 6 inches by 6 inches by 3 inches. So in this problem, they didn't want you to find the maximum volume. They just wanted you to find the dimensions. Are they much shorter than that? Not really. Okay, sorry. So let's go ahead and look. We've got 2 more to look at. If a box with a square base and an open top is to have a volume of 4 feet cubed, find the dimensions that require the least material. So when you see that dimensions that require the least material, this is essentially surface area. So in the problem before, we were given surface area, we wanted to maximize volume. In this problem, we're given volume, we want to maximize surface area. Okay? So let's go ahead and write our primary equation. Our primary equation will be the surface area. This is a square base with an open top. Do you remember the surface area, square base, open top? Yep. X squared plus 4xh. If you can file that away, it's going to save you a ton of time. Okay? And then they tell me that the volume is 4 feet cubed. So that's my secondary equation. The volume of an open box is x squared h equals 4. Okay. So now, if I look in my original problem here with surface area, I notice I've got an x and an x, and then I've got 1h. So you know what? I'm going to solve for that 1h right here. Okay? I don't want to have to put it in twice, okay, for the x's. And so here I'm going to get h to equal what? 4 over x squared. Now this is a big mistake, I'm going to warn you. This gets made a ton. People subtract x squared from both sides. I see it happen almost every year. If you do that and you work through the problem and you can't get it to work, look right up here because chances are that's where you made a mistake. Okay, so let's go ahead and plug in 4 over x squared. So once again, we try to simplify as much as we can. So cancel, cancel. So I end up having surface area equals x squared plus 16, oops. Try to write that 6 again. 16 over x. So now we need to find the derivative. Derivative of x squared is 2x. Derivative of 16 over x. Okay, here's a trick. You negate the sign, and you put it over x squared. So in this case, it'll be negative 16 over x squared. So whenever you have something over x, like if you would have negative 10 over x, you negate the sign and put it over whatever it is squared. So in this case, 10 over x squared. Okay? All right, so now we need to do what? Yep, set it equal to 0. So basically, I'm just going to, oops, I don't want to do that. I was hoping I had my pen. There we go. I'm just going to do this. 0. So I really get 16 over x squared equals 2x. So I'm going to multiply both sides by x squared. It's an easy way to do that. So 16 equals 2x cubed. What do you do now? Divide by 2 first. So I get x cubed to equal 8. So what times itself 3 times will give me 8? 2. So I get x to equal 2. So now I'm going to plug that in up here. So I get h to equal 4 over 2 squared, which h equals 1. So it says find the dimensions that require the least material. 2 feet by 2 feet by 1 foot. Okay, that one went a little easier because we didn't have the surface area problem. Now, we're going to go ahead and push through and finish with this last problem. Okay, and then that way tomorrow we'll talk more about these, but you'll have more work time tomorrow. So let's go ahead and look at this one. It says a rectangular page is to contain 24 square inches of print. The margins at the top and the bottom of the page are to be 1.5 inches. The margin on the left and right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So this is where a diagram comes in extremely handy. Okay, what ends up happening is we have a page of paper here, and then we have our print area here. Okay, this is where our print is. Okay, I'm going to call this X, and I'm going to call this Y. Now, it says the margins of the top and the bottom are to be 1.5. So really, this distance here is 1.5. This distance here is 1.5. So what would be the dimensions of this side right here? Y plus 3, because here's your Y, and you're adding 1.5 and 1.5. Now it says the margins on the left and the right are to be 1 inch. So I have 1 inch here. So what are the dimensions of the bottom going to be? X plus 2. Now, they want to know what are the dimensions of the page so that the least amount of paper is used. Least amount of paper, that's the whole sheet. Okay, so in this case, I'm going to try and maximize my surface area or my area. And the reason why it's not surface area is because it's just flat. It's only 2 dimensions. So I'm going to take my x plus 2 times y plus 3. That's your area. The area of this sheet of paper will be length times width, because it's area of the rectangle. Okay, so let's see what else we say. It says a rectangular page is to contain 24 inches squared of print. So inches of print, here's your print on the inside right here. Okay, the print will be x times y equals 24. How do I know it's x times y? Key, look at your label. That will tell you your finding area. Okay. So now let's solve for one of the variables. Let's just solve for y. It doesn't really matter in this problem because both x and y are pretty much the same amount of work. So now I'm going to plug that in right here. Now this one we're going to have quite a bit of work to simplify before we find the derivative. Because in looking at that, what are you going to need to do? You're going to have to FOIL it out. Okay, so let's start. That times that. 24. Good. Okay, outer term I get 3x. Inner term I get 48 over x. And last term I get 6. Now I could go ahead and add those together, but it really doesn't, I don't need to in order to find the derivative. Okay, because the derivative of 24 is 0. The derivative of 3x is 3. The derivative of 48 over x. Negative 48 over x squared. And the derivative of 6 is 0. So that's why it really didn't benefit you to add those two and then find the derivative. Let's go ahead and set it equal to 0. So I get 48 over x squared equals 3. So multiply by x squared, I get 48 to equal 3x squared. So what do you get x squared to equal? 16. So x has to be what? 4. Nice job. So x is 4. I'm going to plug it in up here, and I get y to equal 6. So it says, what should the dimensions of the page be? So let's go ahead and plug it into our diagram, because this is going to make a whole lot more sense. So 4 and 6. So what are the dimensions of the page going to be? Yep, 6 inches by 9 inches. Now, if you would have tried to do that without a diagram, it would have been extremely tough. Okay, now tomorrow, once again, we're going to continue working. We'll probably work for the rest of the week on this section. Okay, I don't actually have any more examples that we will do in class. So this is what you need to do from this section. Pages 223, 224, 3 through 5, 9, 11, 19, and 20.